Okay, hello everyone. Welcome to another episode of Amplifying F Sharp. We have a very nice session prepared for you today, but some housekeeping before. We are recording this Zoom call, so if you don't like to be later on uploaded to YouTube, yeah, switch off your camera. We do this to have a better resolution because, yeah, rightfully a lot of people have complained about our poor resolution when live streaming. So we will try with the recording and the later uploading this time. So let's briefly talk about last week. Okay, you should be able to see my screen, right?
Yep.
Yep. Okay. Somehow Zoom isn't doing the border thing anymore. So last week we had Jimmy working on a feature he missed in FS Docs. If you want to see a really good professional navigating of a unknown code base, watch this. It was really nice to see how Jimmy navigated in the unknown code base and found his way and yeah, made the first inroads to his desired feature. That was a really good session. And of course, on Wednesday, the F Sharp Essentials lectures started. We were off to a good start. Quite a good number of people showed up. We covered the basics of the basics, which are of course needed to build up the course over the next couple of weeks. So if you missed that one, check out YouTube. You can get up to speed if you missed the first one, or join us for sure in the next week for lecture number 2 with Ian and Edgar. So let's come to today. We have Dave here, and maybe you have heard about the Tiny Systems course from Thomas Petricek. It's super awesome. If you haven't already, check out his videos. Yeah, personally, I can listen quite a lot to this guy. Super nice guy, and his lectures are just great. And Dave here, who will present today, was inspired by the courses to develop an in-browser development environment. Super cool. So with that said, I will give it up to Dave.
Thank you. Hello, everyone. I'm not sure where to start, but I thought I would take you back to the beginning of what I saw of Thomas's course. And we saw the landing page there for the course. And some another F sharp.
Share your screen if you haven't.
Oh, yeah. Okay. Let's do this. So this is this one, I think. Are we looking at a... Do you see my screen now?
Yep.
Okay. Okay, so I think someone else tweeted a link. It might have been Ronald Schlenker. I'm not sure, but this is the stuff that I found that really got me. I found these tasks that Thomas had posted, and they're clearly for his students, but I just opened them up and looked at them and thought, I think I know how to do some of these. So what he would do is, these tasks are fragments of code that you have to fill in order to make it work. And I expect if you watch the videos, you'll see what you're supposed to do, but I was way too impatient to watch the videos. So I just loaded these things up and then realized that I could load them into a Jupyter notebook. And so that's what I did. Um, let's see here. Did I? Yeah, so that very first task we were looking at, I just copied and pasted into a Jupyter notebook right here, and then filled it out until it ran, and did all the tasks. So I copied and pasted them in, filled out the bits. So, for example, if we look at say task 2, at the minute he's not really doing the language. He's showing how to do constraint solving. Oh no, sorry, I'm getting confused with the Hindley-Milner stuff. He's showing how to do the expression trees and that type of thing. But he'll say um, the to-dos are what you're supposed to do. So this was great for me over Christmas, just to, when I wanted to do some coding, I would just fill these things out here. So in this bit here, so we're looking at number 2. Sorry for the scrolling here. Here we go. So he said to add the code for the if. So there you go. I put in what I thought would be the if and tested it. I added some more code to do the test cases so I could run and do the tests. And that's what I did. I would do this every throughout the day or just when I had some time. And I did all 8 of the tasks right up to the very end where he implements lists and things using the minimal set that he's defined of ML. And he has the rudiments of a union and pattern matching, and he does enough of the language for him to implement lists, which just kind of blew my mind. I'm kind of a language geek. I love expressiveness and expressing computation. So if we look here, I've filled enough of his tasks in for him to implement list.filter basically. And he's done it with what feels like nowhere near enough language primitives. I've written toy compilers and things over the years, and I was just amazed at Thomas's ability to show you enough of ML to be able to do this kind of expression. Of course, I was frustrated by the fact that we had, to try anything out, we had to create these expression trees. So this is where the idea came from. I was thinking, well, I know how to write a parser. I'm going to write a parser for this simple language. It's going to look like F# or OCaml. That's what I wanted to do. But if you're interested in things like this, I highly recommend getting a Jupyter notebook up, setting it up, and going through these exercises. They're fantastic. They taught me so much. What's even better is he shows you how to do type inference with Hindley-Milner, which I thought was just a black art. That's just, you've got to be Simon Peyton-Jones or Don Syme to understand that stuff, and that's not for mere mortals. But he does explain it, and I get it, and it's very interesting. So I also did that. Excuse me. If we go up, just go up in Thomas's systems thing here, we can see that he's got TinyHM, which it looks like it's just another one of these languages, but it's actually the type inference tasks. So he shows you first how to do a numerical solver, and then he shows you how to do type unification. And by the end of it, you do have a type solver. So I wanted to bring all these things together, and I wanted to see what would it look like if we could, turn this, this TinyML plus TinyHM into a system I could interact with. So after I'd done the notebook, I when I went about that, I used Sutil, which is my web framework, in order to do the front end. I had created these this kind of UI ability within Sutil to do so that we can do things like these text panes and things. It's a bit like a rider interface. So you can, you can move these panes around. Sometimes this works, sometimes it doesn't. So I can move this pane over here, that type of thing. And so this gave me a way to present all of these things and with the buttons. And so that gives us the basics of the UI. Then one of the most important bits here is that we're using Monaco right here, which seems to be the open source part of VS Code editor. It's quite amazing. So you get a lot of stuff for free in this just by loading this up. So in order to bring this in, this was an exercise in using TS to Fable. And I've done that for previous projects. So I was able just to bring this in. Let's move this back to there you go, there's a bug. Okay, that was the easy way, just refresh the whole thing. So then the next thing I added was this file system. So part of the toolkit I already have is an interface called iFilesystem, which abstracts away the idea of a file system so that I can use it in browsers. And what it's doing here is it's layering this on top of local storage. So all of these things here, which I can just load into this file editor, they're all on my local machine. I can download them. Sorry, they're stored in local storage in the browser. So if we were to, I'll bring this onto, I know you can't see this right at the moment, but there you go. I've just right-clicked and there's a kind of a really badly implemented file system with UIDs and everything and folders all sitting in local storage. One of the cool things I learned about this week was something called indexed DB. And the reason I found out about that, maybe I'll talk about that in a bit if I run out of other things to present, but that would be a better option for using a local file system. So as you edit things in here, it does save them. So if I do print 34, I save that and compile it. We know it's successfully compiled because we get an AST abstract syntax tree over here. And we get a nice message down here. And if I press run now, we get the output from all of these statements. So we can see that we got 34 there. Now, print was probably one of the only things that doesn't exist in Thomas's language because it's the IO part. And I had to build in the idea of built-in functions. So all the experiments I did to see what the language could do are all kind of listed out in these files here. So for example, if we do, I don't know, this is just a quick, a listing out of the data types that we can do. So we have, numbers, booleans, tuples, lambdas, and unions, which look kind of weird at the moment. I'm trying to make them look like they belong to a larger language, but really the unions in TinyML are two-cased things. So I created some syntax called U, as if there was a type like, I don't know, say case one. So you're led to believe that there's that you've defined this somewhere. So this is what the unions look like. This syntax won't compile. It's not known by the language yet, but that's the implication of looking at something like that, I guess. Um, if we can compile this as well. We see the syntax tree over here. And we can see we got the one, the Boolean, the tuple, how the lambda looks, plus some internal types there. You can see we got the source token from the parser right there. And that's just because I'm printing these objects through %A. F# does a very good job of trying to format built-in types and values. It unrolls them, even in Fable. The unit value and one of these case values. By the way, if you want to try this out for yourself, then I'm talking to my local development version here because I'm expecting us to mess around with the code. But you can go to tinyml sutil.dev and play with this yourself. When it first loads up on your machine, it pulls all these files into your local storage. And if there's been an update, you can press reset and it will pull them back in from the main server here. But it doesn't need a server to run. It's more like hosting. It's pushing it all into your browser. Your browser is doing all the work, all the compilation and the evaluation.
Small question.
Yes.
Did you use the usual route of getting the AST and constructing the typed AST out of that, or did you do something alternative to that path?
The compiler I've written may offend professional compiler writers. I think I'm creating an expression tree and then using the Hindley-Milner pass to assign types to the expressions to find the types, not only to try and infer the types, but also to spot type inconsistencies. So any type errors we get come because we've thrown an exception from the Hindley-Milner phase. And what I do from that is I create this generic AST from the back of that phase. And that's where I'm able to click on these nodes. So this might be what you'd call the typed AST. So I see it as expression tree goes through type unification to find types, and then I construct an AST tree, which doesn't really know about expressions, but it does know about source tokens and types. So there's more work to do on that yet. The reason I created this AST as a generic thing is because I wanted to use this environment to explore a more advanced version of TinyML, which has a different parser and different expression trees. And I didn't want to have a dependency on the UI onto the specific types being used. So this AST really is mainly a presentation device. I mean, it can do things as I'm clicking here. I don't know if you can see, but it's showing you what the equivalent, where it is in the source tree. So I wanted to use this to see if the Hindley-Milner stuff had worked, the type inference. So I can see that print has been, actually that's predefined, so that's not fair. We can't say that we've inferred that, but we have inferred that X is a tuple. There you go. So let X, so we do know when we hover over X that is a num times num. So not only is it a tuple, but it's a num tuple. So Hindley-Milner has done that. We can only tell that X is it takes an A and gives an A. It's a form of an identity function. We get to see that X is a unit, and I like this, that we were able to work out that we've got a union here of a num plus something else, but we don't know what it is yet because we've only provided a value, one of the values from the union. We could do a deeper dive into the compiler if you want to see what kind of atrocities have been committed there.
Yeah, I'd be interested. So
Okay. I wonder if I think there's lots to explore. I mean, I think I could spend an hour just playing with the language itself. So for example, here's one of the, yeah, so before we do that, let's look at this. So whenever I do a toy language or anything, I always try and see if I can implement recursion. Can I calculate something non-trivial like a factorial? And this is the exact same expression subtree that Thomas has um, in here. I think it's in the recursion, task number 7. So he's got there you go. So when I looked at that, I was thinking, oh, imagine if I could just write all that stuff just in a text editor. So it's this bit here that kind of, when I saw that we could do stuff like this is why I wanted to be able to create this parser. So that's that same tree right there. And compile and run. There we go. Factorial 6, 720. So that blows me away. The fact that this little thing, just those few lines of code can do this. And then we put the Hindley-Milner and stuff on top of it, and we get to find out more about FAC itself. Let's see. I wondered if we would get partial application for free, and we do. So I don't have operators yet, like so in F# and maybe OCaml you can define infix operators, but we can define, we can map this infix operator into a simple function, and then we can partially apply add and get a function which will add 2 to anything that you pass it. The type of this is now a num and gives a num. And there's no special code inside the compiler that says let's implement partial functions. It's just a side effect of the architecture of the language itself, just the stuff that Thomas has defined himself. And I know it's not him. I know he's just presenting the way ML works. But still, this was a learning. I've often wondered how you do partial application. I've implemented it in my own toy languages. And, it comes down to, I've done things in the past where all functions had, they had any arity from, from 1 or from 0 upwards. But of course, in ML, every function, as in the lambda calculus, every function takes 1 argument. Once you allow yourself that constraint, or you implement that, it's actually liberating. It feels like a constraint, and it might be a performance constraint, but an express from what it gives you in terms of power from the language is incredible. I can kind of see where it all comes from. So, and this stuff just works. So these bits of code here are the things I tried as experiments and just couldn't believe they worked. So I don't know if anyone else shares this sense of wonder, but this is really interesting to me. So this works. That's incredible. So what about currying? So now this is something that I did implement in the parser because I realized that this is how Thomas was presenting multi-argument functions, curried functions inside his examples. You would just define, nested lambdas, chains of lambdas, and you end up with we can see here that sour is, depending on which way, yeah, you can read that as a function taking 2 arguments and giving you one number back, 2 numbers giving 1 number back. And that's just syntactic sugar, really. This is syntactic sugar for that. Internally, we would see that we had, in fact, I think we can see it here. Yeah, we can see that sour and sweet are exactly the same structure internally. So again, a professional grade compiler system may optimize that so that we're not creating functions where we don't need to create functions. But, I like the purity of this, that it just works. What else do we have here? Oh, okay, yeah. So one thing that was really difficult for me, I've never implemented a parser before that did indent-based parsing. White space to me has always been something you just consumed and threw away. It's like background. It's like the background color of any image to me. It is just the stuff you're not interested in. And to bring it into the foreground, to bring white space into the foreground as a significant syntactic token was something I had to learn about. So this is, I've got some notes in the project that explain how that works, but this is just my test for seeing that it does work. There are some oddities to the way I've implemented it, such that things like my if block, it considers the else to be a child of itself. So the else needs to be indented as well. I've had a rethink on that and how I would change that. But it was enough for me to create the parser. I definitely didn't want to introduce anything that was C-like or any cheats that made this more like C rather than ML for the parser, because I could have conceivably invented a new syntax for the language, but I really wanted it to look familiar to people who understood ML and F sharp. So this looks a bit weird, and it's gonna be upset if I put that else there. So the fix for that is that, or use that form. So that's a thing that needs fixing. Then lastly, let's just, well, a couple of things. Let's look at compose. Yeah, so composition, we get the ability, we can define higher order functions that will compose other functions for us. So we can see that compose has been determined to have, takes a B to a C and an A to a B, and then gives you an A to a C. And then you can create these negation functions, these multiplication functions. And then I can create a negx10 function by composing negate and mul10. So when we run this, we get -50. I think that's right. I've looked at it before and verified, and it's right. The other thing I found more recently was a thing called a blackbird operator, which is what happens when you take that same compose function and you compose it with itself. I don't, intuitively, I don't understand what that means. When I read the explanation or look at the type signature, it becomes a bit clearer, but I still needed help understanding it. Basically, you end up with a new function that takes, I think it takes 2 arguments. It's like let's have a look here. Yeah. So we've blackbirded increment and multiply, and then we end up with a function which will is that right? Oh yeah, so it'll multiply 4 by 15 and then increment it. So there we go. So then I wondered what happens if you blackbird with itself, and that's a crazy looking function. But part of me is kind of amazed here that I'm exploring how composition works with this TinyML system. You could do this in Fable in the online REPL, but I'm again astounded that you can explore these kind of calculus level, lambda calculus level inquiries with this simple system. Finally, I went a bit mad with I took Thomas's list implementation, and then wondered how much of list I could implement. So we've got append, map, filter, fold, fold back, and these all work. So the output here, we don't have strings in this language yet, but if you match that output to everything that's going on here, you can see that it is correct. So we're mapping this it could look like F sharp or a camel. What is cool is that I've told Monaco that this is an F sharp program, and so it's close enough that it's applying all the syntax highlighting for me. So, we're getting a lot of what's the word? We're being helped out a lot by the fact that we've implemented the same syntax as F sharp, largely. Any questions about any of this so far before we go and look at some actual code? Okay. Let's get rid of this one. Okay, well, this is the actual source code. This is available on GitHub. I don't know where to start really. We could start at the UI.
Yeah, sounds good.
Okay. So let's go and find what would be the main function, I guess. This is essentially what main looks like in a Sutil program. It reminds me of Fable Elmish, where we do program.makeProgram. What we're doing here is we're creating a Sutil element here and then telling Sutil to mount it onto an actual DOM element. And our DOM element is, by default, it's called Sutil app. So this is the main HTML for the application. We just have one hosting div, a place where we pull in the compiled application. And we're using Vite for this. And so if we go back to app.fs, you can see this is its function here. So the first thing I'm doing is there are a number of ways of dealing with CSS in Sutil, but what I've decided to do for this project was to take in my style sheet, which I've created in. So if I go here is a style sheet that I've defined in code. There are some advantages and disadvantages to doing it this way, but this is how I'm doing it for this project. So if you know any CSS, you should be able to read this. We're applying width, height, and overflow hidden to anything with class container. And what I'm doing here is I'm actually just poking it straight into the style sheet. I'm kind of uploading it as if it had been included. So that's what these two things are doing here. We then create so we're using Sutil doesn't need to use Elmish, but it works. I think it makes a more sane program when it is Elmish. So Elmish in Sutil looks a bit different to how it does in standard Fable Philly stuff. We get a model and dispatch function after doing make Elmish. And then with Sutil, what we're really doing is we're creating static HTML elements. And if you don't make any bindings, it is just static HTML. You need to have bound a store value to mount points in your application in order for it to change. So we can't really see that here, but what you are seeing here is a div plus the toolbar plus the main content. So that's how the main application looks there. We're doing some initialization of the file system. When the docking system initializes, we get a call to this init panes, and we just add these panes in. So this is how we can just add new panes into the UI. So we could do another one. We can call it deep dive. Icon. And this is the fun bit. When we could put this at, say, right, bottom right. This is where I want it to go initially. So content then just takes a sutil element. And what I'm going to do here is just do an HTML div. And let's say is open true. Now this is a list of options. Sorry if this is killing you watching me type this. I thought they were arguments, so let's just fix this. Okay. Okay. And there we go. So, because this is the development one, there's our new pane working. So that's how we can add panes into the UI. And of course, for things like the editor and the log, we have more complex components than that. Let's see. Here's how we're defining the toolbar there. And so you can see that, as you'd expect, we're just defining buttons paired with dispatch calls. I'm using a function here that I've a utility function for doing modals, enables me to do OK cancel type requests to the user. So again, I just pass sutil elements and dispatch functions so it can ask questions. And then we've just got a bunch of view functions here, which are ways of taking model state and giving us a sutil element. And here's how we host the Monaco editor. So when we do a view of an editor, we create a hosting div. And then host is a function within, so with sutil, it's a DSL. So you declare the tag, then any child is either another element, and so another sub DOM element tree, or it's an attribute or an event. Or it's something which just wants to do something with the current element, and that's what this is. So here we're adding an event for on key down to this div, but here we're saying when the DOM element is realized for this div, I want you to call this callback. So it's a bit like is it a bit like ref in React maybe, but this is a real element right here, an HTML element that we then call out to our editor, and we initialize Monaco with this. There's more going on under the hood with that. Let's have a look here. So here's some of the code lens and the hover provider integrations with Monaco going on here. So I haven't done much with the code lens, but that does work. That was pretty cool. So this is where if I've got a symbol and I want to show the type to the right-hand side of it, a bit like what's it called? Ionide does, then this will do it. I've tested this, it works, but it's a little bit irritating the way I did it. But here's a hover provider. We saw this working inside TinyML when we were hovering over symbols. So we were somewhere in, let's see. Yeah, there you go. When I construct this, I ask, I give it a query function to say, here's a position, give me back the suggestions. And so when we instantiate this, further down here, we give it a link into the AST model. So the model here, so if we go and look at the model that's being rendered, no, that's the wrong one. Oh, okay, I know what that is. Let's just go to the top here. So I'm scrolling up to where I'm defining the model for the MVU Elmish stuff. So here we go. We've got a list of the files, whether the current file is modified, but we've also got the current AST. So if an AST is present, it means there was a successful compilation, and the compiled object is what enables us to get the current AST. The compiled object is a bit like a .exe. If we were able to get one of those from the compiler, then we can run it, ask run AST, that type of thing. The compiler is, if there are two compilers enabled, which I have on my local version, I can choose which compiler I want to use.
Could you show the iCompiled object?
Yeah, sure. So a compiled object, it's fairly minimal. It's something I can run and get an AST of and ask the type of. And it's because I consider it to be an expression, a single expression. So even if we have multiple statements, it's still, even a whole file is essentially, and if you think about it in F#, it's kind of the same. From a value point of view, it's a single value. Any values which appeared beforehand have either had to be ignored, or they have to have, you assume there are side effects and they should return a unit, that type of thing. So an iCompiler is something which can give me a result of an iCompiled object or a compiler message list. I've been reading a little bit of theory about how you do. If you want a compiler which can offer suggestions, you really don't want to do this. You want to succeed every time, and you return an iCompiled object and a compiler message list. So what we really want from compile is we never fail. This is what we really want from it. We always want it to succeed, to give us something that we can navigate as far as the parser was able to, so that we can query it and ask it, say, so we can explore that tree that it was able to parse. Obviously, you won't. Oh, sorry, no, this is wrong. This is wrong. No, that's right. Yeah, the run should fail on this compiled object. But I ought to be able to explore the AST as far as it's defined, and then maybe that's where I have the power to see what could be, what suggestions there could be for if I can work out where the cursor is when it failed, I might be able to offer completions there or whatever. One syntax error ought not to make the whole page just lose all its syntax highlighting up to that point, and so on. Is there anything else I can show you?
maybe we can briefly talk about the parsing part.
Yeah. So it's all done with parser combinators. This is a port of F parsec, which I understand to be a port of parsec from Haskell. And it's come around full circle to being called parsec.fs. But this is a Fable friendly port just at the API level of fparsec. So this gives you a really rich set of parser combinators. Parser combinators are something that if you don't know what they are, a good place to go and read about those is on F# for Fun and Profit. Scott Walashin does a great introduction to these. The ability to combine these into powerful parsers is amazing. So if we go to my parser, we could start top down or bottom up. So let's look here. So here we got some basics here. We have a T expression. A T expression is what we're trying to parse at any point. It's the main unit of compilation, or the main value of the compilation phase is a T expression. And let's go and have a quick look at that. What we have here is Thomas's original expression tree, and that comes straight from the Jupyter notebook. So I've really added nothing more to this. I don't think I've added anything else. Maybe constant L, I'm not sure, but everything else is the same. But the one thing I did want to add to it was I wanted to know I wanted a link back into the source tree. So I created this source token object, and then I jammed that together with an expression and called it a T expression. I experimented with all kinds of ways of doing this. This is something I do want some advice on, is how you take something like a discriminated union, and then you say, well, I want every value in there to have a common inherited value like this source token. It makes me feel like going to an object-oriented model where you inherit from something that's got a source token, but I can't quite bring myself to do that. This almost works, but then it infects T expression, then has a knock-on effect that then all the children expressions need to be T expressions too. So I've hit what I feel is like a really newbie type of modeling issue, which I'm unhappy with. It leaves the structure of the expression clear, but the code that was really clean, that was dispatching expression values, now has to dispatch these tuples. So if anyone's got any ideas on better ways to model that, I really would appreciate that. But what you can see here is that when we do parse a constant of an int, because we're going to return not just the integer that we've parsed, we want a T expression, we have to return the source token where it came from. So if there's an error in it, or we hover over that constant in the source code, we can show where it is in the source code or provide a meaningful error message. So there's how we do, that's how we get an integer, a T expression. Variables, these are, I'm taking an identifier parser, and then I'm prefacing it with this not keyword identifier. So it will parse an identifier like let. So let is a valid identifier. Well, it's a string of characters, but a variable means that it can't be a keyword. So that's how you express that. I like that. This operator here is something I created that a bit like this operator, but it magically it's almost monadically. It's almost as if it's treating source token as a monad. in that variable is it's as if source token is the monad and it's a source token of a variable. So it kind of wraps variable as a with its source token value. It's not really monadic, but it makes me feel like there's that kind of hidden chaining of computation going on. Here we can see, we talked about the if then else earlier, so you can see how we when we parse an if then else, we call it breakable, which really means that everything inside here can be put all on one line or have indentation tokens. So it means that WSB means a white space or a break. And I'm calling a break almost like a break in the line, like a new line or an indent. And if that happens, we must be indented to a level greater than where we started the breakable section. And this is why you can see that the expression will be indented after the if, but then so are the then and the else. And that's why the else is treated exactly the same way as the expression. And this is the root of that problem that I showed you earlier on with the if then else. And then you can see that we use we extract the values from the if then else parsing in order to give us a new T expression, which is based on the if. So we've got the if, the condition expression, the true expression, and the false expression, and then the token that represents the location in this source code. We're parsing all of the constructs here. And here's where we do the currying. So we talked about this earlier as well. The let is parsing the let keyword, optional rec to say whether it's recursive or not, then a name, and then an optional set of additional arguments. So we will always have a let A equal something. That's the minimum, but it might be let A B equal something, or let A B C. So here we capture the B's and the C's and the D's that come after the initial A. We get another break works white space break token, and then the equality operator, and so on until we get to the optional in. I wanted that to work like it does in F#. I don't know what our camel does, but strictly speaking, in Thomas's expression tree, every let is followed by an in. But I realized that could be syntactic sugar as well, that if you have let A equals something, then let B equals something, and then an expression, that's a nest of let A equals, let B equals in the final expression. In fact, we can see that in fact, let's just so if we do let A equals 10 in 2 times A, you can see that the AST tree, we have just a single top level expression as we would expect. Let A equals 10, and then here, this is the in part, the final expression, 2 times A. But if I do this, we get the same parse tree from it. It doesn't require the in. It goes through and pulls all these things, hoists them into single expressions. If I did A there, I'm not quite sure, but I think it will create a do block. There we go. Now F# would complain and say you didn't ignore this value. So that's something that you can analyze from this do, because we can see the analyzer for that would say, well, here's so the value of this do block is this one, is this expression here. So anything before this do in this block of do's statements, they must all be unit, or they must trigger an you should ignore value. So that's how we can analyze that. So this is I think what you'd call the canonical form of that expression. And you can see it's a single expression of lets, but we don't have to do it like that. You and I we would all write this like this. Well, I'm making a big assumption there, but that's how I would, or let's say print. So you can see that even though this looks like it should be some kind of do, it's not. It knows that as soon as we start a new let, it becomes the in of this previous let, or the expression following a let becomes the in of the previous let, and so on. It gets pulled all the way back. So we've still got a single let expression here.
We
This
have
is also wonderful for scoping as well.
We have a question from Damien in the chat. He asks, "Is that single file parsec in its entirety? Is it something you mind sharing?"
Say that again, sorry.
Damien asks, he has been seeking a Fable port of parsec. He wants to know, is that single file parsec in its entirety, or is it something you mind sharing, or is it already in your GitHub repo?
So it's in I pulled it into the to the GitHub repo, but because I don't think it's a package, I think it's just on this guy's GitHub repo. So yes, he can have it, but there's like a copy of it in mine, but there is a link to it I think if we go to the README, I think I linked I mean to link to everything that I've used. So I think it should be there. There it is. It's right there.
Hmm.
So it's there, Damien. It's also in my repo as well. So this here, I believe if there's any differences between this file and the one that comes from the other guys, I think I'll try and fix it. But I did add, I added the indentation stuff myself. So parser.util here is a bunch of other stuff I added to sit on top of parsec.fs in order to help to do all the to do the stuff I wanted to do, for better or worse. That's also freely available from this repo. We're kind of out of time. I mean, we didn't actually look at much code, but I hope that was interesting for people. It could be a dry subject. But it's hard to know where to go when looking at so much
No,
stuff.
don't worry, that was super awesome. I enjoyed the last 60 minutes greatly.
Okay,
So,
good. All
I
right.
mean,
Well,
yeah.
if anyone has any questions, please feel free to contact me or download the repo and do what you like with it. So,
There's another question
I've got
from
a question here from Damien. He says, "Do you plan on tackling generics?" I do, and they're kind of already being done because type variables are already built in. It's part of the Hindley-Milner inference scheme. So whenever you don't know the type, you introduce a type variable. And if you mean, can I define types with generics in? Absolutely. I think the framework underneath is already there. I'm sure I'm going to learn a hard lesson as to why that's not true, but I see a path through to doing it. I have some crazy plans for this whole thing, which I ought to progress a little before I talk about them. But they're kind of in the README anyway, I think. Not that README, the one that's on the website. That's the repo README. I would love to be able to. I have a version of this that doesn't just evaluate in its own interpreted loop, because at the minute what happens is when we run this, what we're actually doing is we're just doing a match statement on the expression, and just the way it's done in Thomas's Jupyter notebook. But I've got a version of this which compiles that expression to JavaScript, and I've worked out how to do the source maps as well. And like I say, I've got a prototype of that so that this stuff can actually generate JavaScript. Um, I've got a version also that's got JSX as a native expression, so that you can do things like, so a program might look like this. That could be a valid program in this extension of TinyML. Oh, parser recovery. Oh,
Yeah,
I'd love to. I've got to go and watch that.
yeah, that was an interesting session that we had on Amplifying F Sharp. With as a guest was Eugene from JetBrains. So he did crazy a lot of changes on for F#A, I think, if I'm not mistaken, and they introduced a lot of error recovery in F#. So yeah, the presentation that you are giving us and the error recovery, I think, are the two most interesting for me in terms of learning how AST or what AST was, because yeah. Okay.
Yeah.
Also new to all of these, programming language terms. So yeah, that's good.
Okay. Well, I would look at anything I've done as enthusiastic rather than state of the art. I I I can see what's wrong with my modeling, but sometimes I don't know how to fix it. So, and the more I learn about the way the professionals do it, the more I can improve what I've done. But I do like tinkering and making things work and then playing with them. So that's what's driving me with this. Yeah, and I'd love to do some of the things that Svelte can do. I'd like to, I'd like to extend this to the point where I can write almost. Could I write the UI of TinyML with itself? That's the crazy idea, really. But it's a crazy idea. I should stay where I.
Okay, we will have you back with a second session when you're ready with these ideas.
Okay. Thanks, everyone.
Yeah, great. Let me take over the sharing again. Here we go. All right. Yeah, thanks, Dave, for doing this. Super interesting. At least for me. I'm like you. I really enjoy these these theoretic but also practical gems of languages, and yeah, it's just beautiful.
Thank you.
All right, let's wrap it up for this week. If you'd like to do something like Dave today did, check out our site to get an idea what we do. Check out the YouTube videos here on our page. There's the join us form if you have a particular topic or issue you want to work on. Just get in contact with us. Don't forget the F# Essentials. Number 2 is coming up next week. If you are an open source maintainer and you feel like you're burning out, you can also reach out to us and maybe have a chat with someone who can relate to your current state of mind. And that might help you already. And if you are in the position of running some F# project, some software project, and you think some of us in the crew can help you moving this forward, we are also available for contracting. So reach out if you think we can help you. All right, with this, I will stop the stream